Yeah, so I'm Aaron Trowbridge. I'm at Carnegie Mellon University in a robotics lab, actually, where we work on control algorithms. This is Andy Goldschmidt. He is a postdoc at UChicago, who also works in this kind of robotics-y flavored control for quantum computers. So we do pulse design. We design like the pulses that actually run and control the qubits at the lowest level. Hence, like our logo this year. If you were at JuliaCon last summer in Boston, we did not have this yet. So this was a new design that I thought was clever. I should mention, so Piccolo.jl is a meta package that includes 3 sub-packages. So I recommend, if you're going to check out the documentation, quantum collocation.jl is kind of where the main documentation lives. Name trajectories handles like trajectory data, and then trajectory indexing utils is small but pretty self-explanatory. So like, why do quantum control and why build a software package to do it? So there are a lot of interesting problems in this area. So like in neutral atoms, you might have different design requirements. You might want to build a time optimal gate that kind of rails your control on and off. Or you might want some smoothly changing pulse to control some sort of atom interactions with your lasers. Cat qubits require interesting control designs because they live in a coherent state space, and then also like some recent work on optimal control for readout of these qubits was very interesting. We actually have like tested a lot on transmon systems. So we worked with the Schuster lab that was at UChicago, is now at Stanford. So this QR code will take you to a link kind of demoing some of the transmon tools we've built, which like leakage is a problem. So we heard in the last talk about the qubit space for doing quantum error correction. If you leak into higher levels of your qubits, you actually will not be able to account for those errors anymore. So staying in the qubit space is very important. So like, how do we vision people using this package? Usually you start off with a Hamiltonian description of your system, and you'll construct in our language a quantum system that will basically handle that drift and drive Hamiltonians. You'll also define a goal state, and you can do this in a couple different ways, where you could just say, I want a goal unitary, or you can even do some sort of embedded unitary in a higher level space. You can embed a subspace unitary, so you might want to do this for some of these when you're modeling higher levels that you don't want to leak into, but you want to do a qubit gate. And then you'll build a quantum control problem. So if you guys, anyone will look into this, last year we gave a talk on like what this package actually does underlying. So this is borrowing from robotics direct optimization and solving direct collocation, hence the Piccolo in the name. But basically, you're solving an optimization problem over the states themselves, so the wave function, the unitary, the controls, and the time steps. And you have some objective over this. It could be your fidelity objective, objectives on the controls, whatever. And then also, interestingly, in this case, an integrator that links states at one time to states at a previous time. So this is like a nonlinear constraint that actually enforces your dynamics. So you can actually parallelize over all the time steps in a solver and like put one of these constraints on each core, and you can get a lot of interesting advantages out of solving quantum collocation problems in this way, as opposed to like a shooting great method. And then also you can put constraints on the states themselves. You can put constraints on the controls, time steps, do whatever. You can do very interesting things with the constraints. So how this looks in the interface. Basically, like we have a certain type of problem called a unitary smooth pulse problem. And this handles like designing pulses that have a certain controllable level of smoothness to them by actually bounding the second derivative of the control. So you can pass an abstract quantum system, you can pass your goal state and quantum operator, you tell it how many time steps you want and what should be the size of that time step. And then there's a lot of options for the underlying IP-op solver and also the Piccolo options themselves. So we have a lot of different problem templates that we have set up for users to use based on different problem settings. So smooth pulse problems, bang bang problems, which you want to like basically turn the controls off and turn them off, turn them on and turn them off. Robustness problems, you want to be robust to certain types of errors. Minimum time problems, where you constrain the final fidelity to be a certain value and then solve for the shortest gate you can do, which you can't really do in an indirect method. And you can do in here, which is very cool. And we'll see that later. Sampling problems, direct sum problems. You can do stuff for quantum states as well, pretty much all the same things. And we're also right now working on density matrix control problems. So this is like kind of the main philosophy is like there's a lot of different problem settings that you might want to solve, either minimum time or robustness or joint problems or any of this. You want smooth pulses. So you can do all of that in this framework. You can also, like, very interestingly with the name trajectories, you can kind of like concatenate them together in a direct sum problem and then solve sampling-based robustness problems in this way. It's very cool. And we'll see some of that, I think. Okay, so from last year, we have gone from 0.1 to 0.3. We've added a bunch of new features, including quantum system templates, which lets you create quantum systems in a parameterized way and recreate them with new parameters. Embedded operators for handling the subspace stuff, leakage suppression, utilities for like looking at your Lie algebra space and deciding, like, basically determining if your problem is controllable, so you can actually reach the goal state you want to get to, which is very cool. Theory, and then also a lot of underlying infrastructure for the packages in this package ecosystems, including using testitems.jl to handle a lot of our tests, which we've been focusing on. At this point, I'm going to hand it over to Andy to do a code demo. So if we go this way, we can go right here.
Okay, yeah. Okay, well, in that case, we'll move relatively quick. I have 5 minutes. I'm not going to run a lot of cells. Anyhow, so we're going to start with a really simple system. It's kind of the standard test bed. Yeah, okay, we have way more time. All right, we're like 5 minutes, and we're like, all right, we'll get 20 minutes of material done. I was like, just be ready, we'll get there. Okay, we're gonna take a breather then and do this at a reasonable rate. Okay, so like Aaron described, what we're gonna walk through here is just the kind of core underlying, if you remember in the last talk, like the qubit rotations. So what we have is quantum dynamics, which we're gonna just think of, we've got a linear differential equation, or yeah, we can, yeah, you want to dial up your,
Control plus usually works.
Yeah, it'll increase all the bars, so we're going to actually just increase the editor font size so that way we don't.
Is this better? Yeah, okay. Perfect.
Nice. Okay, yeah, this way these stay tiny. Okay. So if you can see, we have a system which is bilinear in states and controls. And so what we mean is, like, you've got your controls, they're attached to Hamiltonian operators. So those of you familiar with kind of standard linear control theory, that's kind of the subtle difference here. But we can think of these as basically acting as rotations. So you might think of basically doing some sort of kind of control for, quadcopters or things like this will also use these types of methods. And so these rotations we can encode in our framework via quantum system object. So you have, for our case, we're going to just add some drift just to make it interesting. And then we're going to have two controls, so a drift operator and then our list of controls. And we're going to target this goal, which is an X gate here. And then we're just going to take a peek at our quantum system object. So we have some drift operators and then the isomorphisms and some other information in this constructor object here, which we'll talk about. And then some of our Lie algebra utilities that we've kind of been describing. This one's going to be really easy. So we made it verbose so we can just see that the Lie tree is of size 1 because, well, all these matrices are the basis for your system. But we'll look later at some other more interesting systems and how you might use that tool. Okay, so then we've got a system. Let's construct a control problem. We're going to take a certain number of time steps here, and a delta t, system, goal, plug those in, and then we're just going to enforce basically the fact that we have Hessians or not Hessians depending on the kinds of things you want to do. So we're just going to make that very explicit in our options. You see we're adding a ton of constraints, doing a bunch of kind of stuff under the hood to set all this up for you. And now all you have to do is hand this off to a solver. We're going to cap, this is an IP opt option, but we give you a quick way to access the super easy ones you want. We're going to cap this at 50 iterations, run this, and check in on our fidelity. So we got a bunch of 9s. We have some plot utilities that will let you kind of inspect this trajectory object, which is one of the packages. This is a named trajectory. And we see, okay, we've got some population behavior. We basically are doing an X gate, which is a swap. You're just switching the 0 to the 1 by doing a pi rotation of that block sphere embedding that sphere. You're just swinging it around on the x-axis. And so, okay, we got an X gate, but look at all these braided wiggles, okay? So this is kind of an imprint of the initial control initialization. So you see you've got a lot of kind of arbitrary action here. This might be like jostling and kind of bouncing around more than you really need to as you kind of whip around on this rotation. So what can we do? We can mess with things like, let's try a min-time problem. So we can specify a final fidelity. This can be turned off and just use the default problem fidelity. And we're just going to take in that previous problem and reconstruct a new one. And I'm going to add some stuff here basically to just turn off a lot of the printing so we don't have to deal with that. So we'll construct this problem. And then we're going to solve basically minimizing the time subject to the constraint that we keep at least 4 nines. And let's check in on things after 50 iterations. And we see, OK, some of the braiding gone. And if we look here, our total time is 6. Previously, we were more than double that. And if we let this run even longer, we'd get something more interesting. But let's kind of keep trucking along. Perfect. OK, so yeah. I just want to jump in to the next section and say, OK, we had these smooth pulse problems. That's great. That's one category. But control hardware differs. Needs differ for users. And one other setting that you might want to pursue, bang-bang control, which is sort of the like time optimal behavior for these types of bilinear control problems, where you just kind of hard rotate on one axis, and then you switch and you hard rotate on another axis and things like this. And so let's give that a try. And we'll talk about how this is implemented after we see it work. So I ran this for 50 iterations. What I want to highlight is like the solver is really nice for being able to kind of just rerun things and kind of reinitialize. So let's say you didn't get what you wanted with that 50 iterations, so you want to just kind of pick back up where you left off. So we'll just do that, and OK, like now we've caught up to where we wanted to be. We'll go back to our plot utility and check in on what we've got. OK, so now we've got a lot of the braiding. It's gone. Great. And in fact, you can kind of see like that bang-bang behavior. It's on, chilling here, and then off. And in fact, this little drag kind of correction, this is basically just dealing with that fact that we had that drift present on the system. So actually, if you remember in the theory slides, there was that like transmon picture, and there was that like nice Gaussian pulse, and then there was that little subtle correction. That's kind of exactly what we're seeing here. It's just dealing with the fact that there's that Z rotation, and you're just kind of like offsetting that and getting rid of that extra bit of the dynamics because you don't want that impacting your system. So how do we do this? Well, we're flexible in how we design this named trajectories object containing all of the data we're optimizing over. We're doing direct collocation. So states and controls are in this optimization problem. And so that means that like for smooth pulses, we can just directly control with the accelerations. For these kinds of problems, we can directly control with velocity, and we can penalize something like the L1 norm of the velocity and introduce sparsity. So just like a lot of standard tricks coming from control and just making sure they're accessible to the quantum community, getting all the math kind of in the right quantum dynamics settings. So, OK. So those are small. That's the standard qubit things. Let's try to like stay in the qubit space, but just stretch what we can do with that. So I'm going to take a system here, and I'm going to make it sampleable. So I'm just going to define a function. And I want to just remind everyone about our previous fidelity. Looks pretty good. But let's say we apply that on a system that is not at the value that we had this drift here. And the fidelity drops. And you can see it'll like, it'll get worse as we go. So, oh, right, Aaron's weird keyboard. So I'm not going to play with that. OK, so what I'm going to do here is I've just assembled 5 systems, and I am going to coordinate them in one large problem where all the states are separate, but the controls are now shared. So they have to use the same controls, implement the same gate that they're all targeting, and do it for this sweep of systems. OK, so the nice thing here, linear problem scaling, because we're just dealing with a bunch of qubits instead of one qubit. So not really a big demand on compute to get something more interesting. And what we're going to do is we're just going to take those fidelities, and we're just going to roll them out on a whole bunch of those Z values, those errors that we might have been experiencing that we want to be robust to. And so if we look, what you see here is this is the previous solution, which is dialed in at that drift that we had used in the model. But you see the robust solution kind of like bounces around at a few points that we've like included in the samples. And so we now have something which is valid we're like below 4 or 5 nines here for like a much wider range of solutions as opposed to being like dialed into a very specific model. So this kind of model robustness is pretty critical to a lot of the design because a lot of quantum control ends up having to be open loop because feedback is I mean, you just saw that whole talk on error correction. It's a challenging game. We can also sample on the goal. And so what we're going to do here is we're just going to take a rotation of this unitary about this Hamiltonian here. And we're just going to let theta vary for some amount of values. So I'm going to just construct a bunch of smooth pulse problems. And I'm going to do that in a loop for 10 thetas from 0 to pi. And then I'm going to use a direct sum problem to basically glue them together via a regularization on this A value. And I'm going to solve this and then check in on the fidelity of just one of those goals just to see what's going on. So I'm going to take the first control. I just augment these symbols here. And we're not going to have time to talk about how name trajectories works, but it's basically just a container with a bunch of symbols associated with the various parts of the state. So like a classic kind of like named array or something like this, but with some extra help for quantum systems. And so what we're doing here is we're solving now 10 qubit problems together. And so we'll see, we're going to burn a little bit more as we stream and compute at the same time. And so we'll let this run, but like at a high level, basically you can specify anything here and the behavior is going to kind of vary. And you see we put the fidelity constraint, so it kind of pushed right up against that boundary. And we're just trying to keep the controls together. So you see we have these plot utilities that let us kind of specify, in this case, all of the symbols, all the various controls that we are interested in. So these are all for the various angles. And you see that what we've done is we've glued them together. So now instead of having a bunch of separate rotations to different gates, we've kind of got a sweep, right? Which is telling you, okay, I know there's this kind of manifold, perhaps, in control space that's implementing this rotation. So now you have something more interpolatable to realize kind of this family of quantum gates. So that's another feature. And you know, we probably could have turned those off more efficiently. But yeah, so that's one thing you can do. And then this is just to Aaron's point. I wanna just kind of introduce these constructors for quantum systems, which is a whole separate kind of template framework, which we have some access to, and it's a little more relevant when you start to build more complicated systems. So here we're just going to take a transmon, and we're going to have our parameter just be the number of levels. So you see that you build a system just like before, drift, drives, and you construct it now with a constructor, which is just a reference to the function itself. And so when we do that, we can build a system, and then we can re-specify that parameter or like partially specify some of the parameters, update different ones, rebuild the system. Now we have a 3-level system and a 2-level system for this transmon. And so what can we do with that? Well, let's just go back to the reachability questions and say, like, I want to implement this 2-qubit gate, which is basically identity except for in the 1-1 case in which you want to pick up a relative phase. So that's the CZ. We'll check it on a 3-level system, and we'll see, okay, we needed to go up to the 3rd level of the Lie tree. We didn't actually control in the full space, so we couldn't access all unitaries, but the gate was accessible. And we can even peek just to see, like, okay, what's going on here? This is an embedded operator, so it's zeros except for in the subspace. And we can like unembed that operator and just kind of check, okay, that's what the CZ is, so this relative phase is what you want. And if it's not the 1-1 state, so 0-1, 1-0, or 0-0-0, 1-1-0, whatever, you don't have that relative phase. Okay, so what happens if you go back to the 2-level system? Well, in this case, you actually are reliant on that drift to get the relative phase. That anharmonicity is critical for this gate. So you see that if you try to do this in a 2-level system, you terminate in some subspace, and you weren't actually able to achieve it in that subspace. And so just an example of kind of like how these reachability tools kind of speed up your design and iteration as you work through this process. So that is kind of the tutorial we have for this talk, but like I said, we had the QR code. There's another tutorial that walks through like more explicitly like transmon setting, leakage suppression, some of like the very practical stuff we did for like Schuster Lab and things like this. But I think now, just to kind of wrap up, we'll kick it back to the talk on what Piccolo looks like over the next year.
Okay, so what's next for us? We are shooting for a 1.0 version of Piccolo.jl sometime this year, so which is very exciting. So this is basically our game plan for getting to that point. Like in the moment, we're actually working on like open quantum systems. So we have a couple systems in mind that we want to test this on, specifically cat qubits, where you need to worry about the openness of the system. Also, like we listened to Chris Rakoukis's talk yesterday, and we're very inspired to get up on our docs and CI contribution and style guides. So we are very motivated to do that. We've been thinking about this, and then seeing his talk was very inspiring. We also want to integrate some of our higher level like utilities for like creating quantum operators and like Hamiltonians and stuff. We want to integrate with Quantum Toolbox to handle a lot of this, and also utilize a bunch of their tools. So Quantum Toolbox is like the Qtip version of, or it's like the Julia version of Qtip, which is starting to come online, which is exciting, through the Unitary Fund as well. Which I should have mentioned that we are a Unitary Fund sponsored project, which I didn't include the logo on the slide, sadly, but I should have. So Quantum Collocation Core, we want to spin out, like basically, we have an underlying core package that deals with a lot of the solver-specific stuff. We want to kind of separate that out from the higher level interface and land at a Piccolo.jl 1.0 by the end of this year. So just to highlight a few things, so it's great to be in Eindhoven, dankjewel. So if you go to this QR code, this takes us to the GitHub page. We are also like kind of exploring the commercial applications of what we're working on. So we have like our company's kind of called Kestrel, and we're going to be doing the National I-Core, NSF National I-Core program this fall. We are like, I'm in the robotics exploration lab at CMU. Andy's in the EPIC group at U Chicago. We also work with the Schuster Lab very closely. We have a growing user base of people at Stanford, U Chicago, Harvard, Inflection, IBM. We're adding lots of new features, and like we're looking to get feedback and support and see if people want to contribute. So thanks to the Unitary Fund again. I can't believe I missed this thing, and that's it.
Thank you. So how about non-unitary dynamics, Lindbladians, losses? Is that covered?
Yeah. So we are working on that like at the moment. So we're heading in that direction. That's like one of our next things we're gonna do. So stay tuned. Yeah. You'll see some stuff on GitHub probably this week maybe. And if you have any systems in mind that you would like to try this on, like please reach out, and we'd be very happy to try it out and walk you through stuff.
Yeah, that's been like honestly like one of the biggest ways to kind of build out features is getting kind of the right problems, and also because of the problem template infrastructure we're kind of fleshing out, like getting the kind of core, okay, this kind of template matters to this community. Like that's how we've kind of tapped into a lot of like Rydberg atom settings and things like this, like Rydberg problem template I think is what we've got it called, but we've got a few of those in the works for different settings. Effective models and full models,
And I have a question about some design decisions. My main one really is, have you considered quantum optics GAO versus quantum toolbox? What in the trade-off was making quantum toolbox preferable?
So the quantum toolbox package is very cool in that they are trying to like duplicate perfectly Qtip from Python, and like so many quantum people are using Qtip that to give them a Qtip basically interface in Julia is maybe one of the most quickest ways to access that community. Also, they're involved with the Unitary Fund as well. Yes, quantum optics is super cool. We are probably would love to allow for both packages to be accessible. Like ideally, we could allow any like quantum objects from either of these packages to just like be converted into quantum systems. Because like the real use for this is like basically building the Hamiltonians, and like where do you want to maybe roll out your system, test an evolution of your system. But the Qtip Python community is kind of why we went with that.
Like to just add, like I think entry points and exit points for these ideas, like getting rollouts that like you would know like how to implement the right kind of rollout, how it would tap into our framework, like whether that's like the way to go to allow for kind of users to specify if it's going to be
Thank you.
Any more questions? Do you think that I could use Piccolo.jl in the future to test if like a hardware-specific mapping, which I create like for a specific circuit, has a higher or lower fidelity than a different one, or is that out of scope?
So you're saying specifically like if you were to implement a gate like you have a Hamiltonian model and then you're trying to integrate this into a circuit and then roll it out in a circuit setting. Yeah, like some of the work that we've done, we partnered with IBM to kind of like build on top of their Qiskits, like Qiskit dynamic simulators and stuff like this. And I know Qtip has a like open pulse circuit simulator that sort of allows you to plug in pulse implementations. The first talk and Yao and others having like basically circuit level implementations and being able to plug in kind of like pulses, introduce coherent errors, add all that infrastructure would be really nice. So I don't know when we would start kind of that pipeline, but like having those features would be awesome. I mean, there's a lot of really interesting research questions and like practical applications to building that. So.
Also, like in this framework, which is something that's like very interesting is if I go all the way back here. So if you have some like hardware parameter, that would basically be like a parameter that propagates into a model Hamiltonian. You could throw that parameter into this problem and optimize over the parameter itself, which would tell you what parameter you should use on your hardware. So you could basically solve a big problem where you have like some constant parameter in here. So like we have some ideas right now that we're working on with like kind of adding in like a carrier wave frequency for like for one of these pulses. But like pretty much a device parameter you could throw in here as long as it propagates into the model, solve it, and the solver will tell you what device parameter will give you the best result. And solve for the pulse jointly, so it'll solve the whole problem in one go. So that is like something we can totally do. We don't have the tooling right now to do it, but we're very interested in doing this.
Because yeah, back when I started using Julia, it really wasn't good. Nowadays,
So I'm not sure how to put this properly in context, but like, is everything Hamiltonian based? Because in general, in quantum problems, you can also consider wave function deformation. And so do you always need Hamiltonians for your package?
Everything is built around these operators, which depending on like the underlying integrators, we sort of make some structural assumptions to like add benefits, which is kind of what Julia Kahn's last year's talk was about. But that doesn't mean that you couldn't change the integrators, and we've done that to explore other kinds of problem classes like more traditional like quantum chemistry or just kind of like spatial, for example, wave functions. So we have like quantum states that are embedded into the 0, 1, 2, 3. But like we've explored these. I'd say that's still a work in progress for us to decide how these integrators should get most flexibly introduced into this framework. But we've done some problems for this. We just don't have maybe the stability to like release it into public code. Yeah, it's just not quite there yet.
Yeah.
But yeah, would be happy to talk more about what we've done and kind of like, what's missing.
And I think in this framework, what's cool is like the states are variables themselves. So you can like, if you want to put some constraints on like the shape of your wave function or something like this, work in a spatial domain, all of that is very possible in this framework because of the direct nature of the problem. Yeah.
Thanks.
Okay, thanks Aaron and Pickle team again. We'll have the next talk from Stefan.
Beautiful. Thank you.